first to thank the organizers for the invitation, Ivan and all the organizers. So I will talk about the dynamics of solution to the damped inhomogeneous nonlinear Schrödinger equation. So about my affiliation, this is University of Tunis Manar, and actually I'm at New York University at Abu Dhabi, and this is the center. I'm a research scientist there in a site which is center of stability and turbulence. So it is my first visit here in this center, IMAS, and the university, even at Mexico City, and all the Mexico. It is my first visit here. So this work is joint work with Lasad Alwi and Sirin Jberi from the University of Tunis El Manar. So this is the plan of the talk. I hope I will time to address all these points. So let me begin. So we will consider the following nonlinear Schrödinger equation. Here there is a potential K, which we may say that is a coefficient in front of the nonlinearity, and it may be real or it may have complex value. And delta here is a positive number. It is a damping term. So for the particular case when delta is equal to 0 and K is a constant, we obtain the standard nonlinear Schrödinger equation, which is equation. And for the case of delta equal to 0, this is the inhomogeneous NLS time potential K. And in this conference, it will be possible to consider in particular the case where K of X is some complex constant X to the power minus B, or it may be also taking some decay but is regular, and also it may also have some singular decay at the origin and some another decay at infinity. So here sigma B, B1 and B2 are positive, and mu is a complex number. So for the inhomogeneous nonlinear equation, it is considered by many mathematicians, and in particular, we have assisted to the nice conference given by Campos here in the audience. It is also considered by Merrill, Raphael Spizel, but they consider a potential K of X, which is bounded uniformly by some Q1 constant strictly positive, and at the same time it should be finite, so no singularity. It is also considered by Fibishi, Wang and Liu for some regularity for the potential K. And for the case K equal to mu and delta positive, it is the damped nonlinear Schrödinger equation, and it is considered by Tsutsumi. This is the reference. And these equations appears in diverse branches of physics, such as nonlinear optics, propagation of the laser beam, and in also, so I give these references, in particular in some case K of X is the inhomogeneity of the medium. And Fibish, in his paper here, note that the damping term or the absorption term plays an important effect in the physical model, and it should be considered in the equation. So the aim of this talk is to study the impact of the potential K and the damping delta C on the local existence, the global or the blow-up phenomena of the solution, and to study the asymptotic behavior, in particular the scattering, the existence of solution that scatters. And in particular to say to unify the what is known for the NLS and for the damped inhomogeneous NLS. So I will start by few remarks about local existence, and for the standard NLS equation, which given by this equation, here K of is just mu and delta equal to 0. We have this existence result that say if alpha, the nonlinearity, is smaller than 4 over n minus 2, we can look at n is greater or equal to 3. The problem is well posed, and meaning that for any initial data in H1, there exists a unique maximal solution of the nonlinear Schrödinger equation, which is continuous up to this maximal existence time, taking value in H1, and which can be interpreted as it is C1 in H-1. The proof of such existence is used using the Duhamel formulation of the equation. Here, Et Laplace is the free Schrödinger group, and it is given by this expression, which the convolution with this kernel. So, for the NLS equation, and I consider just here the homogeneous case, there is some scaling. So the equation is invariant by this scaling, and looking for the norm of the initial data for the solution rescaled, we obtain something here, some S minus S square, S critical, which given by this expression. And we are interested to see the local existence in the Sobolev spaces HS when S is positive, smaller than n over 2, and it is greater than the critical SC. So we will consider S positive smaller, and B here should be smaller than n to have someone which is here is an L1 lock. And we will need that if S positive greater than this, alpha should be smaller or equal to this quantity. So how to construct the solution? So here we have the Duhamel formulation, here the linear part. And the first thing to think is about looking for L infinity solutions taking value in each one. So for the linear part, we have this equality. So no problem for the linear part, but for the nonlinear part, due to the presence of this term, in the case of K is bounded, we have to intercept, even for the K, say K bound, we have to intercept with another space. And when we intercept with another space, for the linear part, say in LQ, LR, we have to find something like this to control with the norm of U naught in L2. So by scaling argument here, this has some scaling, we end up that there is necessary condition should be satisfied by Q and R, which is this one. And this one will bring us to the streetcar estimates that are known for the free Schrödinger group, given that this inequality holds if Q and R satisfies this property with this equality. And for the second term, or for the inhomogeneous term in the equation, we have this streetcar estimates going from R1 R1 P1 Stirkat pair to R2 prime L2 P2 prime, where R2 P2 are Stirkats, also pairs. And these Stirkats estimates are established by Stirkats in 1977 for the case of Q equal to R, and by Ginebra and Viro for different cases, and by Kiel Tau for the critical case when Q is equal to 2 and R is equal to 2n over n minus 2. So for K bounded, we have we did this nonlinear part in this manner. We have some integral, but in fact, what we here we use just K is likewise a constant, so it is bounded. But for the inhomogeneous nonlinear Schrödinger equation, we cannot do this framework. In fact, the potential K in this case cannot be estimated in Lebesgue spaces, as it does not belong to any Lebesgue spaces. So there is many existence results that are proved for this potential, starting from Genoux and Suyart, 2008. They prove the local existence of a solution, but writing that x to the power minus b is divided by this part. It is some Kata function on the ball plus another Kata function, and they use this property to and some abstract result of Kazma, and they were not able to treat the critical case, and there is no regularity of the solution. After that, using Lebesgue spaces, there is results given by Guzman in nonlinear analysis. Here I write n greater than 3, but there is results for n equal to 1 and 2, but still not treating the critical case. And recently, also after by Dean, he improved the result of Guzman in the case of n equal to 2. And to treat the critical case, it is considered by Kim Lee Seo, but for S here, and for H1 also on this paper, but these estimates are based on Stirkat's estimates with weighted Lebesgue space. So they consider that to try to reach the critical case, to consider weighted Lebesgue space. But there is no blow-up criterion, no continuous dependence, and no unconditional uniqueness. So this is some remarks about the proof. So they consider these weighted Lebesgue spaces with some weight, which is, and then they show some gamma Schrödinger admissible pairs here. So the problem is that the many things are still not done with respect to the standard nonlinear Schrödinger equation. So after that, we propose a different approach with Alwi, is to handle the singular potential with using Lorentz space. These Lorentz space are used in the talk before, in a nice talk given by. So I will give a definition of this Lorentz space. So here this distribution of distribution function is the rearrangement, and consider P between 0 and infinity, Q between 0 and infinity. The Lorentz space with two index, the first index is P, the second is Q, is all measurable functions such that this quantity is finite, and this quantity is given by this expression. Here, the case of Q equal to infinity is given separately. It is also can be defined with equivalent definition as it is the interpolation, real interpolation between L1 and L infinity. L1, Lebesgue spaces, and L infinity also. This for P greater than 1 and Q greater or equal than 1. So the potential x to the power minus b is in fact in this space, Ln over b, and b should be smaller, strictly smaller than 1. This can be shown by this calculation using this function precisely. And in fact, as said by in the last conference, if I take LPP, which is similar to LP, I can give a refinement of the Lebesgue spaces with this. So LPP, it is given by LPQ1, which is with Q1 smaller or equal to P, and so on up to LP1. So we have a refinement of LP space. After we having this Q2 greater than P, then the Lebesgue space is increasing with respect to the second index. So we have also Holder and Young's inequality, and we can define this Sobolev-Lorentz space. Sobolev-Lorentz space is all temporal distribution such that this operator is instead in LSP, I add here Q to D to say that this quantity is in the Lebesgue, the Lorentz space LPQ. And the same for homogeneous Sobolev-Lorentz space. Another thing that we know that we have this Sobolev embedding, but using Lorentz space, we can improve by this space, L2n over nt minus 2, comma 2. Another thing that these Lorentz space, with respect, they have the same property as the Lebesgue space for the scaling. So we have this equality, and the second index does not intervene in this scaling property. And Kiel-Tau proved the Schrodinger's estimates in Lorentz space in 1998. So for the linear part, we have this inequality, and for the admissible pairs, we have this inequalities. The thing that change here, we have gamma 2, here we have gamma 2 in the space, okay? Now, so using this approach, we can give local existence result. So we will fix two quantity, a gamma rho pair. This quantity, as you see, seems to be complicated. Here there is S, B, but how we determine gamma and rho, it is just to consider this operation. Here is the nonlinear part, and we require that we apply this from this to this space. We determine rho, and after that, as gamma and rho as a streetcar pair, we find gamma. So the result is the following. So we consider n an integer greater than 1. It is a complex number. S is smaller than n over 2. And for the exponent p, we have to suppose that it's strictly positive and smaller than those two, minimum of 2 and n minus 2s. And then we can reach the critical case. In fact, this is due to this Lorentz space. And we show that for every initial data in HS, we can find time strictly positive depending on U naught, and a unique solution in this space, here LQ log on this interval, such that this solution has all this property. It is it is unique here. It is in all streetcar space, and we have some continuity property here, and a blow-up alternative. In particular, this blow-up alternative is maybe if you take b equal to 0, we find the same thing. Then, for the global existence, we have, with respect to the smallness of the initial data in this in this norm, and if the max is finite, we have this blow-up rate of the solution, and in particular, we have that more than the blow-up alternative, we have here that the solution blows up in this norm, becomes infinite, and we have a lower bound estimate of the maximal time of existence with respect to this constant lambda. We can write this, in fact, in the norm of U naught in H dot S. Sorry. So, Joe, just some comments. The result still valid for b equal to 0, but because in this case, taking b equal to 0, we have ln over 0, it is L infinity, which is just L infinity. We obtain more regularity here instead of L1, which L1 is greater than 2. We obtain the solution is here. And the proof is completely simple with respect to other proofs, directly using handling Laurent space as this was handled for Lebesgue space. And we also prove unconditional uniqueness. What does it mean, unconditional uniqueness? Meaning that the solution is unique in this space. We can prove that we can remove this auxiliary space. This space is used to construct the solution, but we can remove it for the uniqueness. So, maybe some word about the proofs. In fact, we are not obliged to take k equal to 1 or x to the power minus b, just to k the potential in this space such that the gradient of the potential in the case of S equal to 1 in this space. And as a issue, we have to choose the admissible pair and apply Streetcar estimate and the fixed point to construct the solution. After that, we show the uniqueness here, and we deduce that we have uniqueness in the whole space. By construction for the case S equal to 1, if alpha is here in this range, then Tmax depends on the norm of U naught. In this case, we can show that Tmax depends on this norm. And if k is real, we have taking value k of x is real values. Then we have conservation of the mass. And here there is usually global existence. And we have conservation of the energy. Here is the energy. And we can distinguish two cases, the defocusing cases when k is positive. No, when k is positive, the energy is conserved, and this quantity is positive, so it is bounded. And the focusing case, when k is negative, then the sign of the solution, the energy can change. So for the global existence, also we can give this diagram. So for the defocusing, here we have usually global existence. For the focusing, we're using Gagliardo-Nuremberg inequality, and we can show that here we have a global existence, but here there is a lot of a problem. And there is an example of a global existence if U naught is sufficiently small in each one. And we can construct blowing up solution for this case. And we are interested in the complex case, meaning in our results, we will not consider necessarily k real. So I will now turn to the global existence for oscillating data. So for the case k equal to constant Cazenave and Wissler, introduced some example of oscillating data. So taking taking phi, multiplying phi by some factor, dx squared, and they show that if d positive large, then we have global existence. So in this case, they introduced the notion of rapidly decaying solutions, meaning that the solution becomes in some space LA in time and L alpha plus 2 in space. And A is given by this expression. So they show this, if this is small, and if alpha is greater than alpha naught and smaller than 4 over n minus 2, we obtain existence. What is alpha naught? It is the positive root of this equation. And we can verify that alpha naught is in fact smaller than 4 over n, and it is greater than 4 over n plus 2. This also, some results are also given by Tsutsumi about this alpha naught. So, for our case, we introduced the following positive number. So this is var rho, and this is A. So the value of var rho is determined to allow that this map apply L rho Q onto L rho prime Q over alpha plus 1. And using this, applying for the free Schrodinger group with this dilation, this is to respect the equation, we find this property with A and rho. And we have to choose A so that this is invariant by scaling. And in this case, we have to impose that 2 over A plus n over var rho is equal to 2 minus B alpha. So once we have this, we have to show some streetcar estimates for non-admissible pairs. And what these the streetcars for non-admissible pairs. So we consider zeta and var rho as unadmissible pairs, and we have to choose A greater than zeta over 2. So we have A, we have zeta, since we have this var rho. So we can see that in this case, for the streetcars non-admissible estimates, which is given by this quantity, okay, here is A and var rho, and here is another A and the same var rho, but the dual part of A star. And to have A greater than C over 2, this is equivalent to have some alpha, A contains alpha, greater to some alpha naught B. And the alpha naught B is in fact the positive root of this equation. And we can verify that alpha naught B is smaller than 4 minus 2B over n, and it is greater than 4 minus 2B over n plus 2. So for B equal to 0, it is the Strauss exponent, which is the alpha naught for the case of NLS. And for B equal to 2, we know that B is smaller than 2 strictly, but if we take B equal to 2, this is 0. We have alpha 0 is solution, but we have alpha 0 is 2, but the other solution is, the other is negative. So the positive root will give this. So the result for the global existence is the following. So we take n greater than 4, q greater or equal to 1, and u naught in each one, and we suppose that alpha is greater than alpha naught b. Then we can find some epsilon strictly positive, such that if the initial data satisfies this inequality, then U is global. And we can find these estimates also for any RP streetcars norm. So for the sketch of the proof, we have to apply two things. The first one is the streetcars estimates with non-admissible pairs. And here the epsilon is exactly the linear part, which we do nothing other than we put that is smaller than epsilon, and this is the nonlinear part. And after that, we apply the streetcars estimates with the admissible pairs, and we do so Gromwell argument to obtain the global existence. So some examples about this initial data. The first one is to take phi in each one, sufficiently small, and here we have to add the supposition or the condition alpha is greater than this quantity. Then we obtain global existence in R. In fact, the condition we impose, which is on 0 infinity, will be verified on all of R. How to do this? So we have the Sobolev, and by the Sobolev embedding, we have that this is this norm, and Sridhar's estimates give this quantity. So to handle A, which is greater than Xi, we should have this condition, and by interpolation, we obtain that ET Laplace phi in the L var rho is dominated by this quantity. So if this is small, this will be small, and we obtain the result. Another thing that if phi also satisfy this property, with this condition is sufficiently small, and here we can go up to alpha naught b, we have the global existence. So this is the explanation using this decay estimates for the free Schrödinger group. And we can obtain this inequality, and giving that this is sufficiently small. Now, we can also consider initial data in sigma. This is the space sigma, so that phi is in each one, and x phi is in L2. And using Alder inequality, we can show that sigma, in fact, is included in this space. And we end up also with that if phi is sufficiently small and alpha greater than this quantity, we have global existence. Also, for the case of these oscillating data, we can show, as shown by Kazma-Weissler, but here we have to change with B, since the spaces we are considering are with some B, and to obtain that we have a global existence. So this follows by this inequality, so that this integral converges, and when D goes to infinity, this goes to 0, and we have global existence. For the particular case, also this case, we can show that we may have global existence for positive time, but blow up in finite time for the negative direction. Now, let me go to scattering results. So here the definition, solution will scatter in some space X. If we can find a final state phi plus in the space X, such that this limit holds. In the case where X is H1, we can, since in the case H1, this norm is the same as this quantity, so we may write this, but in sigma, this is not possible. So to show this limit, we have to find the limit of exponential e minus t Laplace of ut, which is written in this manner. And what we do, we have to show that this has a limit in H. We have to show that when, likewise, it is a Cauchy sequence in the Banach space, so that Z have a limit. And to handle this, so we can use Sridhar's estimate or Sridhar's estimate with the non-homogeneous part. Now, for this, what we do, we show some criterion of scattering. So the first one is that if U is a global solution in S1, and if we have, the condition on K are both, if we have that U multiplied by this potential is in LA, L alpha plus 2, infinity, then U is in all the Sridhar's norms or for admissible pairs. U scatters in each one, And if U naught is in sigma, then also U is continuous taking value in sigma, and it scatters in sigma. Now, another scattering, another criterion, instead of putting some potential on front of U without potential in front of U, but if we impose that gradient K is also in the same space as K, then we can show that even for dimension greater than 1 and B here, we have this criterion so that U is in all the admissible pairs, Sitkart's admissible pairs. And U scatters in each one. And if U0 in sigma, U scatters in sigma. So using this criterion, we can show that, in fact, the solution constructed with this small norm, since it becomes in these spaces, it is global and scatters. And we can apply this also for some K, which is taking this value, K, if 1 over plus x squared, it is in L infinity. And so since it is in L infinity, we can apply known results in a nonlinear for the standard nonlinear Schrödinger equation, that we have scattering here, and in sigma we have scattering here. But if we take attention to this quantity K, we can show that we have scattering in fact here with this in the whole interval. How this can be proved? In fact, we can prove more. So we have here a corollary which say that if we take K like this and alpha here, then we have to distinguish 3 cases. If alpha is greater to this, we have scattering in each one. And if alpha is greater to this and U0 is small in sigma, then we have scattering in sigma. And if alpha is greater and U naught is given by this oscillating data, so we have global existence and scattering. So what is the idea? It is simple for the example there to look that K has different, in fact, different decay. It is bounded, but it decays at infinity as x to the power minus 2. So we interpolate all these decay, and what we do, we fix alpha here, and we choose appropriate B so that we have this inequality, and we apply the result with this B. So in fact, if B is equal to 2 or greater than 2, but say sigma, we can reach alpha 0 of 2, which is equal to 0. So also we can consider the case when K has different decay and have some singularity. We can obtain some result, and we show that in fact the local existence is affected by B, which is the singularity, and the scattering is affected by B2, which is the decay at infinity. So nothing other than this alpha 0 is in fact decreasing with respect to B. So we can, if we have more decay, we have a large value of alpha giving the scattering. Now, for the defocusing case, say K equal to this quantity exact, we have also scattering, but here we do not need to impose that the initial data is small because we have global existence. And what we have to show, we show that in fact the initial data, the solution satisfy this decay. And for this, we have to find some decay for in the case of the defocusing case. And this decay will allow us, so here we are up to alpha naught. The result is known for this alpha, but alpha naught is strictly smaller than this quantity. And we show, in fact, it is here, and the U with this power is in this space, and we apply the criteria of the existence. And in fact, these results are improved to attend alpha, the case alpha equal to alpha naught, and some other properties. So I don't have now time to explain all this, but I have to move to damped ENLS. And for the damped ENLS, I will fix K here equal to this quantity. Some results are valid for more general potential, but I will concentrate on this value of K. And for delta equal to 0, so and B equal to 0, there is many results of the global existence and blow up. And there is also some result of non-scattering given by Barab, that if alpha is smaller than 2 over n, this is for the case of mu positive. And the question is the impact of the damping. And here, the L2 norm is not conserved, as for the standard case, delta equal to 0. Neither the energy is not conserved, but we can find another quantity, which is h of t, which is conserved. And in fact, we have exponential decay of the L2 norm, provided that the solution is global. And the energy is negative, starting from negative energy. The energy, if mu equal to 1, we don't know the sign, and so we cannot deduce what is known or not. So for defocusing case, mu is positive. So we have this is positive. So we have good decay for the energy, and we can show that in fact the decay of the L2 norm and the energy is bounded using this H function. So there is no blow up of the H norm. And in fact, the solution exists globally, and we can show that it scatters or in this manner. Here we have delta, so the scattering is explained with this property. How many times still for me? 8. So for the defocusing case, we can show this result. And sorry, I will skip that. And maybe this is an interesting result that we show that if the global solution satisfies, first of this, V, which is equal to this quantity, which is U multiplied by ET delta, is in these spaces. L gamma and rho are the same. Then V and U scatters in H1. And in fact, we have this decay. We gain some decay here. The proof is given also by Sedkar's estimates. And this is the proof. Maybe I skip using this criteria of scattering. And for the focusing case, we have this quantity depending on the alpha. Here we have this, for alpha strictly small, we have this quantity. For alpha equal, we have to add some hypothesis to have this global existence and this property. And for alpha greater, which is more important, for alpha greater, so it is here, the case when B equal to 0, which is considered by Fibonacci, and when he considered initial data present only one hump, he showed that, in fact, the time existence is increasing with that. This is delta, the damping, and this maximal time of existence. And he showed that it is, in fact, increasing with respect to delta, the maximal time of existence. And there is a conjecture given by Fibonacci showing that if delta is, there exists some delta star, such that if delta strictly smaller than delta star, we have blow up, while if delta greater than delta star, we have a global existence. And for the maximal existence time, in fact, it is conjectured that it is monitoring, But recently, on 2007, these authors, Bess, Karls, Mozor, doing some numerical study, show that, in fact, if we take 2 bumps, the maximal existence time is not increasing. It increases, and sometimes return, and after that, it re-increases, and it is not monotone. So what we do here, so there is a result by Ohta Todorova showing that the existence of some, so that Tmax is equal to infinity. What we show here that we find lower bound of the lifespan, and the lower bound of the lifespan of the solution, of the maximal solution, is given by this quantity. Here, beta is some constant, and delta is the, again, then there is some log, but still only a lower bound of the lifespan. And in particular, if delta is greater than this quantity, then we have a global existence, meaning that maximal existence is finite. So we have how large is delta to have global existence. So for the proof, is nothing, it is not really complicated. What we have to do, just to do the fixed point argument. And instead, to say that this quantity h of t, which is given by this expression that is in L infinity, no, we have to exploit it. And to do the argument with this h, this function, what we calculate, and we find that the maximal, we find the local time of the construction of the local solution, and this local time should be Tmax is greater than the local time, and we obtain the estimates of the, this is in the case in R2, and for the blow up, and I think it will be, so still 5, 4, 5. Okay, so we have to consider this quantity. So the energy I have already defined. This is the variance, and this is the integral. And we have these blow-up results. They consider 3 hypotheses. The first one, that the energy is negative. The second one, that the energy is equal to 0, but the variance is negative. The third one is energy is positive, and the variance is negative. So there is known results, in particular by Tsutsumi, in the case of b equal to 0, and we have we have that Tmax is finite, but I think there is an estimate of this Tmax. And what we do here, we found upper bound of the lifespan, and we distinguish 5 cases. So here, the energy U0 is the energy at the initial data, and here where we can take delta tilde is related to delta by this quantity. So but to simplify the expression right here, we have these different asymptotic, different upper estimates of the blow-up time. So just I give the idea. So the idea is to find some estimate about this quantity, but this quantity is positive, and we can show that it is smaller than this function, depending on delta tilde. And when we show that this function becomes negative for some t, so the solution should blow up before. And we have these estimates. So these are some references, and these are some points. The first one is the optimality of the decay rate. We obtain some decay rate with alpha plus 1a. The second one, we don't know, exploit really this decay on A. For example, assuming that we do not impose some radial assumption in some case. The second one, we don't find this delta star. It is known only numerically. And last, this lifespan seems to be more complicated, and in fact is not monotonic. What we find as the lower bound, it is in log, and it is in fact not non-monotonic with respect to delta to the damping, but it is only a lower bound. So we do not know what happens for the monotonicity of this lifespan. It is not monotone as proved numerically. They consider typical example. All the paper is given by, is considered only numerically, but rigorously how to prove this, it is not clear. So thank you for your attention. Thank you for that.
Thanks for this nice talk. So any question? Yes.
Hi,
Hi.
thank you for this nice and interesting talk. And I'm not very familiar with the terminology. I just want to know if you can explain a little bit what do you mean by a blow-up of solution, and if this has something to do with what is called a resolution of singularities.
Yeah, blow up the solution. So we have the local existence of the solution, or the solution, the existence of maximal time of the solution, and the maximal time that it is maximal to be in some spaces, meaning that at some time we cannot measure the solution in this space, meaning that if it is normed space, we say that the norm goes to infinity when we approach this time. The other one, what is the?
I think you have already answered. If it has something to do with resolution of singularities, but I think it has nothing to do.
Yeah, some
Some sense?
We obtain some singularity. The profile of the solution became singular at some points. Okay. When approaching this time, maximal existence time.
Okay. Well, thank you.
Yeah.
Hi, thanks for the nice talk. So your dumping is linear, right?
Yes.
Could you also do some nonlinear dumping?
It is interesting, but here we don't consider this. If we consider K complex, for example, I return to mu. This mu, we can write it as mu1 plus I mu2. Separate complex and the real part. And maybe this, but the problem is this with the same power, alpha u. But in general, no, we don't consider this damping with nonlinear damping.
I think physicists, they look at this, right? They have the Gross-Pitayevsky equation modeling a both gas. And then because of three-body recombinations,
yes,
some particles are kicked out of the condensate.
Yes, yes.
Modeled by, the damping term, which is quinting.
Ah.
Maybe this, there's a nice play.
Maybe, yeah. Thank you.
With
Yeah, I see. Thank you.
Any other question?
I would like to ask about the D star conjecture that you had in the sort of the end of your talk.
Yes.
Can you, what would be the conjecture that you would have a global existence then for which alpha, and for small initial data, or what would be the condition?
Yeah, the conjecture is in the critical case. It is
the critical case.
The
yes.
critical case, which is by Tsutsumi, by Fibishi. Yeah, the critical case here, it is in R2, and here the power is 2. And he conjectured that for delta small, starting from blowing up solution with for the NLS, so we can go with delta up to D star, keeping the blow up mechanism, but after D star, there is global existence.
This all assumes small initial data, or large enough?
No. The initial data is taken in each one so that we have blow up with delta equal to 0. So.
Yeah, thank you. Okay, yes, now I understand.
Any other question? Well, if not, I have one general one, in fact. Are all these nonlinear Schrödinger equation, when there is a blow up, it's because of the space the norm explodes. So we could have, for example, have a creation like a delta on some spaces, and you could imagine having looking at the same equation with a larger space, including delta, like a measure space of measure, and then you could have a global existence in this with the creation of some delta somewhere. And do you know if there is anything done in that direction for kind of nonlinear Schrödinger equation?
You mean delta?
I mean there is a blow up, which, for example, could be an accumulation of mass in one part of the space, and so this can see intuitively as some delta appearing, which is a manifestation of the blow ups, and so you could try to have something which is more general in such a way that this delta is some part of some spaces.
Yes. So first of all, for the blow up, it is maybe related to this nonlinearity. Related to this nonlinearity, looking to the equation as, say, an ODE equation. There is no Laplacian, just the E dtu and the nonlinear part. So this may produce some blow up, in particular for the nonlinearity U alpha U. Now, if you look for the initial data, if we take an initial data which is such as the Dirac mass, we can also produce blow up of the solution. And this is maybe a combination with the nonlinearity and the fact that the Dirac mass at the origin of some other points produces this blow up phenomenon. So there is, it depends on the coefficient of this delta, so the mass, and to give also a blow up. But maybe there is not a lot of study about this, as I know.
I think I heard once, but I am not sure that there is they use like Grosz-Tayachi type of equations. It's mean a nonlinearity with alpha is equal to 3, and then they show that there is a blow up, and so it starts with something which is regular, and there is a time which is positive where it's blow up in certain norm. But then it's able to extend this as in another space where there is a delta appearing, and then there is the remaining part is still fine, and this delta could be interpreted as a manifest of the creation of the condensate for this kind of model.
Thank you.
I think I heard something like that a few years ago. But
thank you. It is interesting. You may give me the reference.
Yeah, I can give you 2 names, but I mean 1 name at least about this as a reference. I don't know. One has to look. Okay.
Thank you. Thank you very much.
Okay, thanks very much. So if there is no more questions, so let's thanks the speaker again.
Thank you very much.
And in few minutes.